PyMonk today, this is a Python package that can be used to create interactive kinematic simulations in 2 dimensions. So that's going to be your basic physics concepts like projectile motion, forces, energy, momentum, and it's relatively accessible. So it can be presented to students in such a way that they can modify single constants in order to get a deeper intuitive understanding of the physics concepts that are being presented. Additionally, by using computer simulations in place of physical labs, you can explore more intricate systems, so you can add more moving parts than you might otherwise have access to. You're also able to ignore things like friction and air resistance, because when we are covering these concepts, we do that implicitly, but trying to do that kind of experiment in the physical world, you'll find that you can't just make friction go away most of the time. Additionally, sometimes when you do a lab, there's just a lot of random noise depending on the specific experiment you're doing, and that can be eliminated with a repeatable simulation, since all of these will behave in the same way, assuming you put in the same inputs. So this PyMonk is a Python package. It is coded in an object-oriented way, so it provides classes like space, body, shape, and constraint. So our basic approach is we're going to construct objects that belong to those classes using the provided constructors, as we'll see in a little bit. Then we can change the properties of those bodies or objects. So change things like their mass, their moment of inertia, their friction, elasticity. And there will also be methods that allow us to do things like apply forces to those and so on. Now, an important note, if you're going to use this in a classroom setting, the units in PyMonk are arbitrary code units. They do not necessarily represent physical values, although the documentation does refer to their time unit as seconds, but that's not a literal interpretation. So as such, it's not important to try to use something like 9.8 meters per second squared for your acceleration due to gravity. Although around it, not like, although a lot of examples will use values that are close to real world values or resemble them. As such, it's much more important to make sure that you're choosing values for your variables and inputs that make sure the simulation is understandable. It's not moving too fast, it's not moving too slow. As opposed to trying to use exact values from physics. So the most important objects, the most important concepts in PyMonk that we're going to be talking about, one is the space object. So as I mentioned, PyMonk is 2-dimensional. So this will be the 2-dimensional region in which our simulation takes place. I'm not aware of any limits on the size that are innate, but usually you'll only want a couple hundred units just because that's what's easy to display. You'll also want to set the gravity. It defaults to 0 gravity, which can be what you want if you're simulating a top-down system, like if you're looking at something on a table. However, if you want to look at something side-on, like say a pendulum, then you'll want to set a value for gravity, in which case x would be 0, and you'd want to have a negative y value to represent a downwards gravity. So the next important concept that we need to talk about is the body. So this is fundamentally objects. So this will contain a lot of the physical information about some physical object in our system. It'll have information about the mass, the moment of inertia, which will define how it responds to rotations, and some others that we'll talk about in a little bit. Now, another key thing about these is that they can be static or dynamic. By default, they're dynamic, which is usually what we're going to want. This will allow them to move around freely and react to the various forces that get exerted on them. However, if you want to make something like a table surface, you can also change it to set it as static, which will be a body that is stuck in place and can't move. And then once we've created a body, we'll need to give it a shape. This will define the physical extent of the body, like is it a circle, is it a square? Things like friction are also stored in this object, which would allow us to control how objects slide against each other. And conveniently, it is using the same model of friction that we teach in introductory physics courses, where it's simply proportional to the normal force of, say, a table pushing back against the object that's sliding against it. Now, if you're using this not on the cluster, which is probably what you'll want to do, we're only really using it here for convenience so that we have a common system to show this off. However, it's a straightforward process. You can simply use pip install, or if you're using conda, you can use conda install, which will handle all that stuff for you. Okay, so we're going to get started, and we're going to use just a simple simulation of two balls colliding in a two-dimensional space. And we'll go back over those fundamentals that I mentioned earlier. Now, doing this sort of collision experiment in a simulation does have a couple advantages. One that I mentioned is that we don't have to worry about friction slowing things down and skewing our results. We don't have to worry about how uneven or not level the surface we're doing the experiment on is. So we'll go through that code. As I mentioned, the first thing we do is we construct this space. And then after that, we will need to construct a body. And as I mentioned, we give it a mass. For the moment of inertia, we use the built-in function to let our simulation, to let PyMonk calculate a reasonable value for us. It's possible to input a manual value, but it's not always trivial to find a value that makes sense without just calculating it, and it is required to get your simulation to run. We need to give it a starting position, which will be just off to the left in our simulation, as we've set it here. And then, of course, we have to give it a shape. In this case, we're just going to use straightforward circles. And we also want to set an elasticity. We'll want to be able to control this because there are several different interesting physical scenarios we can represent here. And here we just set one to use for the same value to use for both with a convenient thing here. Of course, we have to set the radius of the circle. And then finally, the critical thing is that we add it to the space so that it shows up in our simulation. And then, of course, we can do the same thing with a second ball. We started about in the middle of the simulation. And then, of course, we added this ball to our space. Then we start setting up our the figure for the animation. So we start a figure, set the axes. A lot of this is going to be pretty much the same for all of your simulations for the most part. Another important step here is that we need to apply an impulse to our first ball to get it moving. So this function will apply an instantaneous force at time 0 to the ball to get it moving. There are also functions to apply like continuous forces over time. It's generally not recommended to set an initial velocity or to change velocities directly in PyMonk. It can lead to strange behavior in your simulations. So now we'll run this. And we can see that the ball goes off. And because these balls are equal mass, we see a perfect transfer of the momentum. And because we have the elasticity set to 1, we see that the energy is completely conserved and they simply bounce off each other. And as I mentioned, we can manipulate this elasticity to show different things. If we set this to 0, we'll see that the objects stick together when they collide. And if, say, we wanted to represent a superelastic collision, we could set this over to 1. So this would be, if you have 2 carts colliding and one has a spring-loaded plunger that pushes against the carts when they hit, as I remember doing in high school, we can do that as well. And we can see they recoil from each other in that case. You can also have unequal masses. You could give the second mass its own starting velocity, and so on. You could also set them off at an angle and see how that changes things. Now, an interesting thing with simulations is that while we can ignore some of the factors that we'd encounter in the real world, we can also choose to simulate those if we want. We could add in a damping in the space, or if we wanted to, say, do an experiment on a slope track, we could do the same thing. Say if we wanted to slope our track off to the left, we could add some gravity in the negative x direction, and we can see that the balls are acting under that force. So now we'll move on to another example of a simple pendulum. So this will allow us to explore the idea of connecting different objects together. So in PyMonk, this is done using a constraint object. Specifically here, we're going to use one called the pin joint. So this will connect 2 bodies together in a way that represents a perfectly rigid massless rod. So this will force the 2 objects to stay together with exactly the same distance at all times. So we're going to do a fairly similar thing as we did before. We're going to start with the same way we establish our space. Here we're going to establish a downwards force of gravity. And we're going to start off with a ball as before. And then the interesting thing that we're going to do here is we're going to add the constraint, the pin joint. So here we can see that this is going to connect it to the space itself. So space.static body is just a fixed point in space, which is represented in the space's coordinate system here. And then the other end is going to be attached to this body here, the pendulum mass. And then a critical thing to note is that the attachment points are given in the relative to the objects that you're connecting to themselves. So here, since we want to connect to the center of our pendulum mass, that'll be the origin 0, 0 there. So we can see we connect to that there. And then since the point we've chosen to define will start it directly below the pivot point for the pendulum, we'll need to give it an extra impulse to set it swinging. And then when we sent that running, we see that we knock it off to the side real quick, and it continues swinging. And at all times, the pendulum remains a fixed distance away from the pivot point. And then since we don't have to worry with about some of the factors that can make this various differences in the way a student might start the pendulum swinging. Normally, when students do this experiment physically, it's important to keep the pendulum swing fairly small so we can use the small angle approximation and keep things in keep the math more simple for introductory physics. But you could explore more easily what happens in a wider angle, since all of that will be consistent here. And it's possible to start seeing how that turns into a more sinusoidal relationship between the pendulum's length and the periodicity if you wanted. So now we'll iterate on this idea and show off what happens if you want to do something like a double pendulum. Now this is an experiment that can be fairly tricky to do physically in the real world. If you construct a double pendulum using some masses and string, it can be very difficult to try and make sure that the movement of this pendulum is only in 2 dimensions, which is how in classical mechanics courses we'll normally start out doing the math for this system is in 2 dimensions. As another thing that's commonly done with this sort of system is analyzing the fundamental modes, and it's not always easy to reliably get a pendulum swinging in a way that shows those off, but here we can find them and set them from initial values. And since these simulations are deterministic, we can be sure that every time we start this simulation, we will have the same outcome from the same initial values. So this simulation will start as before. As I said, it's pretty much an iteration on the single pendulum. So we start out with that same first mass, and then we add a second. And this pin joint is, instead of connecting to a static point in space, we'll be connecting the 2 bodies together. And here we can see we've connected to the center of both masses. And then it's not necessary, but at first we're going to start off getting both of the masses swinging, so we can see what that looks like. And then we can see that this is a pretty chaotic system. If we change the initial conditions of this setup, we can see very dramatic changes in how this system behaves. And as I mentioned, we can also explore fundamental modes. So for that, we're going to choose to, instead of applying initial forces, we'll set it swinging initially, and then we can get pretty close. So this is one of them where they're swinging together in sync, and you can see we're doing the small angle approximation here. And I don't have it exactly perfect, but that can be dialed in, and you can find other modes. So another interesting, a common demo in introductory physics courses is for projectile motion. It's sometimes called monkey and hunter, but the basic idea here is that we'll have some projectile that we're aiming at a target, but the catch here is that the target is released from rest at the exact same moment that the projectile is released towards the target. So the question posed to students here is, where should this projectile be aimed in order to still hit the target, which helps build intuition about how objects on Earth will always experience the same acceleration due to gravity. And the outcome, of course, being that the projectile should be aimed precisely at the starting point of the mass, whereas students will often come into the course with an intuition that they should be leading their target and aiming below it. So to set up the simulation, of course, we, as always, start off with our space, gravity, our two masses. Now, if we note the starting positions that we set, the angle is at 45 degrees to connect between them. So the force we apply to this ball initially is going to be at a 45-degree angle. We run our simulation code, and we can see that when we run this, the target is accelerating downwards, and we can see a parabolic arc on our projectile, and of course they meet at a point, and our projectile hits our target dead on. So the last example I have here is going to be another type of oscillator to demonstrate another constraint object. This one's going to be a mass on a spring. However, there are lots of introductory physics demos that can be done using springs, so this will be a very versatile object to learn for us. It's going to work similarly to the previous pin joint constraint object that we showed off. So if we look at the code for that here, we can see that in this case, we're going to connect again to a fixed point in space. And then we're going to connect the other end to the mass that we've set up. But we also have some extra parameters here. These are the rest length of the spring. So that represents, of course, how long the spring would be if you're applying no force. The stiffness of the spring, representing, of course, the Hooke's law. So this will be how does the force change as we stretch, how does a force on the spring change the length of that spring? And then if we want, we can also set a damping parameter to the spring if we want to show off damped harmonic motion. So if we set that to 0 here, we can see, of course, we have our mass on a spring and it's oscillating back and forth. And with the damping set to 0, it'll continue the same oscillation, indefinitely the same amplitude. However, if we turn that up, we can see that it won't reach the same point again. It'll be slowing down this motion. And then a somewhat more advanced concept here is underdamping, critical damping, and overdamping. So if we start, if we turn the damping way up, we can see that while the spring is initially perturbed by our initial force from its resting position, that force is going to be, or that motion is going to quickly decay back to the rest position instead of oscillating, which is something that's useful in the real world for things like shocks and so on. Other options for damping are, if you want to do sliding motion, you can do friction. Another is that you can apply a damping to the whole space. So we can see that if we do that here, the pendulum won't reach the same point in its arc. So this will work by applying a constant multiplier to the velocities every, the documentation calls it a second, although that's the only reference to a real world physical unit that I saw in the entire documentation. So of course you don't want to set that over 1 unless you really want objects to be accelerating constantly with no forces applied. And then one extra note that I want to make is I want to talk about this extra loop here real quick in the animation code. So this loop will run extra simulations or extra time steps on the physical simulation side that aren't displayed. So you only need so many frames to show off motion on a screen that humans can perceive as motion. However, it's oftentimes helpful to simulate the physics with a finer grained time step, because in the real world, essentially what we're working with is an infinitely small time step, but we can't do that on the computer. So in some scenarios, you'll encounter strange effects if you're simulating physics with a too coarse of a time step. So like a common one that shows up is that in collisions, if an object is moving too fast for the time step of the physics, objects, instead of colliding with each other, can end up just completely passing through each other, because initially the objects are moved in accordance with their velocities, and then collision code is run to make sure that objects aren't overlapped, and then they are pulled back outwards. So if we're moving too fast, the objects will be completely past each other before that code has a chance to fix things. So that is what I had to talk about. So I'll hand it back over to Guillermo. Stop sharing.
Okay. Thank you, Patrick. So that gave me a perfect opportunity to move into a more advanced examples, materials. And in this time, I will not be using the Jupyter Notebook. I will be using another library that is associated with PyMonk. It's called Pygame. So for that, what I will be doing is start sharing here. I think it's this one here. Okay, so let me see. Okay, so what I will be doing here, I am on Thornyblatt. And what I'll be creating is a terminal, sorry, a desktop, a virtual desktop here. So I will be using here Thorny desktop, standby, couple hours, 4 CPU cores, that should be enough, and hit launch. By the way, I posted on the chat for those of you who want to download the material. You can reproduce everything that I'm doing here. Also, the Jupyter Notebook that Patrick just showed us is right there. And let's see what. So this is what you get when you execute Thorny desktop. And I will be raising a little bit the quality of the image here. By default, is a little bit lower. And I will be hitting this to launch the desktop. So the idea here is that I will be using a library that will actually create the window where I will be visualizing my demonstrations, my demos. And let's see how we can. And the idea, what I did was to create the process of development of the scripts or of the code step by step. So you will see an incremental building of the code and the effects that has on the outcome. So here, if you go here if you download the repository, you will get this. And there is a folder called code. And here, well, we have the materials from our previous lesson from Shiny. And also there is a folder here for PyMonk. So this is the folder I will be using, and I will be storing as Patrick showed us with particles, balls, and that, but I will be evolving into many body interactions, so that is certainly new compared with the previous. A little bit more complex, because at that moment it's you should be using something like object-oriented programming, otherwise it will be a pain. Here you have all the codes. They are progressing from the 1 to the number 10. So a higher Python code is just an evolution of the previous one. And we will start with the very first here, and we will discussing, before discussing PyMonk, what Pygame does and the templating for working with Pygame, which is a library also in Python for producing for making games. But what I will be using is the coupling PyMonk, which is my physics engine, from Pygame, who will be the displaying engine. In the case of Patrick's notebooks, the displaying engine is Matplotlib, because he was using Matplotlib and some interactivity that Matplotlib offers for Jupyter. So now I am doing something else. I am using Pygame to make the displaying of the objects, and just PyMonk will take care of the mechanics of the physical integration of the objects. So this is my very first code. So this is still not PyMonk. There is not import for PyMonk here. This time what I'm doing is, well, I'm declaring a few constants here, because I would like to make this I'll give you the opportunity to change the resolution. I keep the resolution low because I'm working inside a desktop, a virtual desktop that has a lower resolution. So the window, it will be too big if you try to do it with a higher resolution here. But nothing prevents you to change this kind of values. And here I just use a normal VGA resolution, the old one. So here, this is kind of a template to work with Pygame. Again, what you do with Pygame always is initialize and finalize. Everything in Pygame should go between those two calls here, and the display is the area where you will be putting your objects and showing. And here the first thing is to declare this function that will react to some events, such as to execute, in my case, Command Q to leave, or just the closing of the window, some event that triggers the quit of the window, and which will normally and correctly shut down the application. And here I am updating this with a certain clock speed. So if I want something, 60 frames per second is a good resolution for our purposes. So this is our first program. Let's execute this. And for that, we need to load lang Python. And here, let's execute this one. Python 3.01 Pygame display. Sorry. Okay. Python 3 and this one. Let me see. Okay. Okay. So this is our first application. Nothing is just a black display with the resolution that I want. You can ignore the the sound engine. I'm not using that, so I am getting some warnings about the sound engine not working, not being present. You can ignore that. So don't worry about those messages. So now this is the first one. Let's go to the second one, which is whatever we wrote before and a little bit more stuff. So we will progress on that. Now this time I am importing Monk, PyMonk. As Patrick mentioned before, and this is the way of building the body. So there are two things that we need to build: the body and the shape. So the body, it will be here. This we just need to declare. What I'm doing here is I'm using the resolution of the screen, and I am making it. I am positioning the particles relative to the to the size of the wing. That's one thing. Another thing that happens is that Pygame understands the origin of the pixels, so the pixel 00 on the top left corner of the window, while PyMonk understands this origin of the pixels, so this pixel 00 as the lower of the left bottom of the window. So we need some translation for that, and that's something that I will integrate here, exactly here. So this function is making that translation. When we need the coordinates for Pygame, we are just making this change of coordinates, basically. So this is an extra function that I put here. So body is here. This is the body. I am putting down like 10% on the lower corner. That's what I want. And the shape here. So there will be a circle in PyMonk, and I associate a density, and I am adding at the end as to the space here, because this is something that Patrick also mentioned, the creation of the space and the association of adding that body and the shape to the space. So that's it. After that, what we need to do here inside the simulate function, everything is exactly the same. What is new here? Well, I am painting the window white. It's beautiful. It's better. It's beautiful. It's just something that I'm doing here. So white is 255 for red, 255 for blue, 255 RG green and blue. So RGB. So the numbers there will represent how much of that color. So filling all those to 255 will produce a white. And here I am making that conversion from PyMonk positions into Pygame positions, and I'm drawing a circle here, and the circle will be pure red in those positions, exactly in the pixel that Pygame will associate with those coordinates. So that is what I'm doing here. So let's quit and let's execute it. No, sorry, it's always Python 3. So now we see here, I create a ball. The ball is static. It's just, let's say, 10% from the bottom, 10% from the left. That is the position that I'm associating there. So now let's move to the next one. This again is then our next evolution is adding gravity to the particle. So it is right here. So after building the space, I am adding the gravity. Again, here, the units that we are using are pixels, and the speed, or the speed here is pixels per second. So everything will be related to pixels. So if you try to put this in units of space, it will be extremely slow, because you will be putting the units in meters or second square. So it will not work. But well, it will work just too slow, because now you are thinking that 1 pixel is like equivalent to 1 meter or something. So it will create the simulation extremely slow. So that's why I have -100. So it's pulling the particles down. And here I am adding this body that will go on the bottom. No mass, it will be static, no change to that. And what I will do in here is creating the ball and the shape, putting that we already saw this. This is my function for changing coordinates, pi mount to pi gain. And I'm drawing the circle here. And we will see what we get here. So this one. So the particle escape. I build the bar, but I never add the bar, so the floor to this. That's the next thing that I will be doing, putting a flag. Otherwise, the particle just go, it still exists, but it's invisible. So now let's go to our next step here, is adding the floor. So here I have, everything is the same. I add gravity. I think I never changed anything. The body is here, but now I am at the floor. So I call it floor body. This is static, so it will not move. And it will be a segment. So just a line that is covering the entire length of the bottom of the screen. So on 0, because in pi gain, in pi mount, 0 is the bottom. And here I am adding the body and the shape of that of my floor. And here now I have 2 functions that I need to call here to update. I need to update here the circle every time that the position is changing. And I also need, regardless that I'm not moving this, I still need to display to draw the line for the floor. So let's execute this one. And I will be adding this. So Python 3. And now we have a floor, but the particle just hit the floor and stops. So there is not elasticity here. So the particle will not bounce, will not, of course, it will not roll, because the floor is perfectly flat and the particle is falling perfectly vertically. That's one thing. So let's move to the next one. We are adding more stuff here. It's adding a tiny slope for the floor. So the floor will allow the particle to move a little bit when it hit. And also we are adding elasticity, something that also Patrick demonstrated with the balls, and he showed us a little bit what we get. So I am adding something that is high, relatively high. Remember, 1 is perfectly elastic. 0 will be perfectly inelastic. So I put 0.9. And the other thing that I'm doing here is that my shape here, the shape here, it starts in 0.20, so 20 pixels high, and it goes to 0 pixels on the right bottom of the floor. So it has a tiny little slope that allow me to show a little bit this for you now. And here I am also converting from pi mount to pi gain my positions, my coordinates here, for making also in the visual representation the slope of the object. So this is what I'm doing here. And let's see the effect of that. So now I have the particle, and the particle start bouncing, but also start falling across the slope. And you see, I put it this small gravity on purpose, so you see a particle moving slowly. You get the idea. And now let's move on and start evolving this. Let's put more stuff here. And now I think now is this. You see, oh, sorry. This will be the same, but I would like now we have big changes to introduce here. Even if this simulation will be exactly the same, producing exactly the same effect, but I need to re-engineer a little bit my description of the code. And for those of you who are not familiar with object-oriented programming, I will stop a little bit describing what we have here. The idea is that I am moving this into having multiple objects of all kinds. It will be very impractical to do that in the way we did, where we are describing one particle, and after that we need to describe another particle, another particle in sequence. So in that case, it's better to move into what we call object-oriented programming. In object-oriented programming, the functions become methods, and variables can also belong to an object. So an object is basically a class is basically a collection of variables and functions that now are called methods. And those methods naturally will operate with the variables associated that belong to the class. And objects will be just instances of a class. So that is the code now looks different, but pretty much we are preserving the basic ideas here. Everything that we did with the ball, which is adding the body and the shape, now is in the constructor of the class. This method here, it's a very special method, is the init method or the constructor of the class. Each contains the mechanics that will build the object. So we will fill the properties, the variables that we need for this object to be populated correctly, based eventually on some input. So the constructor could have some inputs here, and some of those inputs, as typical in Python, could receive default values. So that's exactly what I'm doing here. In my case, I'm now also reinterpreting what I understand by X and Y as relative positions of the particle in the window. So what I'm doing here is the values of X will go from 0 to 1, and that will be multiplying the width of the window. And the height, it will be also from 0 to 1, and it will be scaled by the height of the window. That way I could change the size of the window, and everything will be fine. Everything will be preserved. And now if I put 0.5, 0.5 will still be the center of the window, instead of having to change all those values all the time. So that is one thing that I did. This is pretty much the same. Another thing is that now those variables are belong to the class. So when a variable belong to a class, we put this self at the beginning, meaning the variable radius that belong to the class ball is this. And each instance that we create of a ball will have its own radius, its own body, its own shape, and a draw method. So now we are also doing something that is very important in object-oriented programming, is that we are putting all the functionality of an object all relatively close together. Nothing that before we have the creation of the ball in one place, and the position of the description of the ball in one place, the description of the shape, and down below on Simula we will have the lines for drawing the ball, drawing the circles, drawing all the object. Now, instead of that, we are creating a class that will take care of that. So now we convert this into a draw method. Same thing for the floor. So, and you will see why I did it this way in a minute. We will be evolving this code over time. So I have the initialization, the constructor of the object here, building this, and now I have my draw method here that will be using again the conversion of unit of coordinates for Pygame and drawing the line. So this code, now I am building my ball here. So this is how you build one instance of a ball and one instance of a floor with a specific position. So 20% from the left and 50% from the bottom. That's exactly the meaning of these two variables here. And it will create a ball there. And also I will be building my floor, and my floor right now is generic. I will be evolving that in a minute. And here inside my simulate, I have my draw, calling the draw methods for the ball and the floor. So if you go here and let's execute this one, it's the effect is exactly the same. I have not changed the behavior of the program. I just remanufacture the way, the logic of the presentation of that using object-oriented programming, which is very important. And you will see when you start making hundreds of objects and moving all those around. So now let's go to our 7 code here, where I will not execute it yet. I will just present it to you what we are doing with it. So everything pretty much is the same. I have now my class. I told you here, my class is right here. So yeah, I never touched the ball itself. And now I am introducing a few changes to the floor. In particular, I am having here the ability to put an angle to the floor. So I can decide, before we have this in parentheses, nothing. So we have no control on the end. Now we have control from the constructor to change the angle. And I am assuming that the angle here is in degrees. And I'm making the conversion, the proper conversion from degrees to radians, which is what we actually need to convert to put it correctly and compute the height on the left and on the right. And also I am making it the possibility to make a shift on this floor, so lower or raise the floor at will during the creation of the floor. And now this time still I will create in one floor, 30 degrees and 100. This is still pixels, unfortunately, but I was lazy for this when I keep it pixels. Yeah, but that's it. So I will be executing this one. And now you see 30 degrees, and this ball now is bouncing and it's going. So yeah. Now let's evolve this, and now we will see more floors, more stuff. And this is a new direction. Now, here, I am not changing ball. Floor, same thing. I have the angle, the shift. What I'm doing now is having the possibility to put, like, if the angle is positive, I will be, well, actually, if you think mathematically, it would be the other way around. A positive angle, it will be a negative slope in this case, and the negative angle I understood here as a positive slope. So basically I'm making here that you saw before, but then also if the angle is negative, I am making like a positive slope in the mathematical sense. So with this, I am now, I did this because now I am adding 2 floors here of this. That's one thing that I'm doing. Another thing that I'm doing is that now I am adding 400 balls here. So for making that, I am creating a list, an empty list. And here I am using the class to create new instances of balls with random locations. And my random locations on the x-axis. And I am shooting with this that all my balls remain in the half top of the window. Otherwise, it will be below the floors and they will go away. So I just raise those a little bit and I am building my floor. So 2 floors here. So you see 30 degrees, 30 degrees. You will see why I did this, what I would like to present. So you see all those balls, 400 balls, some of them just fall away from my floor. The floor has limits, it's not infinite, so it will, the particles will escape. But the nice thing is that, okay, I put this 30 degrees on one side, 30 degrees once on another side, so I have 120 degrees, and that allowed this to create a perfect hexagonal packing for perfect balls. That's one thing that I suggest. If you take the code, start trying to see another alternative. So change the angles and you will see what happens in the angle is not 120 degrees. You start having defects in the lattice. Another thing, well, in this case, I was very lucky, but it doesn't need to be that perfect. Sometimes from time to time, you see they will probably accommodate. So you see the creation of some defects. All those things you can enhance, you can change those. So you see here a vacancy, and that vacancy and a few defects around here. So you see that depending on the values that you put for the elasticity, that means how bouncy will those particles will be. Well, you increase the probability of those things happening or not, or you are quenching the particles too fast. So this is still very classical, but it's still we start getting some ideas about packing, about the behavior of those particles. And so now I am moving into the next one, when now I am changing 09, doing something that introduces a concept for a little bit, which is, what about changing the particles when they collide? For that, I need to add more richness to this. So in this case, now I have another variable here that I will be controlling. It's a variable that belongs to Paul, which is the color. By default will be red. That's one thing. And now I have here the driving the circle, and instead of fixing the color, I am allowing to put the color of that ball based on the color that variable has at that moment. And here I have a function that will change the color. It will swap from red to blue for the color of the particle. And the logic of all that, so floor is exactly the same. I'm not changing floor here. So floor is what we had before. So now I have exactly the same. And well, another thing that I'm doing is I'm having now this promoted into a global variable, 400 volts, because I was exploring when I was building this code, if I should use more or less volts in my simulation, forget the effects that I want. So now everything is pretty much the same. All those balls originally will be red, but now I am adding a new thing in PyMonk, which is a handler. It's a handler is something that you create for the space. So here, and I am adding handlers based on another property that is here, which is the collision type. The collision type. So collision type is an integer here that in my building here, when I build in the particles here, the collision type of each particle will be different. That is another way of saying I will need an identifier such that when two balls collide, I know which two of those balls collide. We have 400 balls, and we need, okay, is the 21 and the 27 or whatever, which of those balls collide. I will be using that in the collision handler. And I will basically, okay, I will create, of course, the ball will not collide with itself. Those are very, very classical particles. So there is no self-interaction or something like that. And so I am making all the handlers that I need to account for the collision handler for ball number I with versus ball number J, and the other way around. And what I'm doing with that is that when it detects the collision, it will change, it will call this function, it will call this method, sorry, it call the method associated to the ball I, and here is the method associated to the ball J here. So what it will be doing is that I will be cycling. So here, not here, here, if the color is red, I will be sending the ball blue. Otherwise, it will reverse the color. So it will be cycling the colors on each collision. So that's something that is like a nice effect that because I will be introducing something else. So it took me opportunity to present handlers with this. And this is what I'm doing now. So you see all those balls when they start colliding, even if the collision is very tiny, invisible, they're still colliding. At some point, they stop colliding. They will. So you see over time, of course, they are losing a little bit of energy with each collision because the collision is almost elastic, but not perfectly. So all those, the kinetic energy of all those particles is going down. And at some point, they just remain with a certain color from the last collision that they produce. So that is what I'm doing here. And that allows me to move into the final version of this, where I am simulating the cooling of the particles. So what I'm doing here, okay, everything is pretty much the same. The balls are created here. Okay, what changes is the draw function here. I will not, I keep the handlers, but I will not be using that. What I'm doing now is that I'm computing here, I'm capturing here for the body, the velocity in X and Y direction. With this, I am just computing, well, the square of the velocity. I call vel, but this is actually the square of the velocity. So I will get this positive number. If the velocity is too high, I will be painting those balls red, meaning they are hot. They have high velocity there. But otherwise, if the velocity is not that high, it's lower than 1000, what I will be doing is transitioning the color of the ball from red to blue, meaning that if it's close to 1000, it will be very, very red and very little blue. If the particle has a very small velocity, it will be it will be bluish. It will be less red, more blue. That's what I'm doing here. So I am associating a color that goes from red to blue for my particle here. What else I'm doing here? I think everything else remains the same. I put still the collision type. I put the handlers, but I'm not doing anything with them effectively. And that's it. So let's see my final version of this. Is this. So you see very hot particles, they quench very quickly. And the only particles that still have some velocity are those and the borders that still jump a little bit, but they are getting cooler and cooler. And if you change the value, for example, of the elasticity, you will see the balls quenching very quickly, or if you put them perfectly elastic, I think most of the balls will escape. They will jump all over and escape. Oh, thank you. I am very glad that this is giving you ideas. So now let's move on to another example. Patrick already presents something like this, so I'm pretty much reproducing this for the chaotic pendulum. So let's work in the double pendulum, which is really nice. And I will start with this. So this is now tutorial 2, the folder tutorial 2. So I will be a start. This is I start with this. Assume this like a template, something that you start with this. You put it. You don't need to understand a lot of Pygame, so you can Pygame mostly for creating games. But I'm just using it for my plotting purposes. So this is basically all that you wrote for Pygame related. So is this, and the understanding that you need to change the coordinates. So this is pretty much the same thing as the first example. And if you like, well, to execute this, it will generate the typical black screen with nothing inside, very boring. So just a boring empty word. And now I am doing this. I am start adding things here. So the space. So this is something, again, Patrick introduced us to the space here. So space is around here. And here I am the space, adding the increments of the space on 1/60, which is okay. We will see. These steps become important at some point, because the idea here is more demonstrations, not simulations. I call them simulation, but you need to be careful what you mean by a simulation in the strict sense, especially when you are dealing with highly non-linear cases, chaotic cases. You need to be very careful. By all means, we are not dealing with symplectic integrators or something really, really sophisticated. And so energy will not necessarily is preserved, but not for any. It just computationally is not so curated for, or is not intended to be that precise. So now what I'm doing here is adding PyMonk. So, well, of course, I add PyMonk, we put the space here, so we have that. We have my traditional, almost traditional ball class here, but again, the positions are relative to the positions on the window, and the density, all that is pretty much the standard. I did a small change here. I put the ball here inside the simula function That's another possibility. I did it differently this time. So I put it here, 2 balls there. I don't think that I have gravity here. So no gravity yet. So just the balls. And I'm drawing those balls. Oh, perfect. So what we have here is just 2 balls. Just 2 balls. Right there. So now what I will be doing now is putting those balls and adding the springs, the bars, the change that will join them. So what is here? So here pretty much is the same. Ball remains the same. So those are balls. Is this new class string here? And Patrick also showed us this here, this pin joint object that we are creating, for which we are associating 2 bodies. And here I am using something that is very Pythonic, which is allowing this attachment to be 2 things. See, I got. Okay. Put those allow attachment to be 2 different things. One, it could be a body, because in my pendulum, one body could be attached to another body. And another way is that I could understand attachment to be a position. So that is the logic that I'm doing here. If the ID that I have for this, and I create the string or the bar, it's not it's a rigid string, is a body. I understand that the second body is this attachment variable here, and otherwise it will be creating a new body for that position here. So I will be taking attachment as a tuple that contains the positions where I will be creating the body. And this body, we don't need to care too much about it because it's just static. So it's basically saying my body where the first pendulum is attached is just like a nail. I am clamping the string with a nail into the floor, into my space, and that's it, period. So that is my second body in that case. So I'm making that a join here, and I adding here the object to the space. And here I am displaying, for the displaying of this, displaying the coordinates of a line between the 2 positions. And the simulation will create 2 balls. And I put them in a different position because I would like to show something. So I raise them in a very specific place. So that is something that's slightly different. And here I'm making my string, well, the first string, which is when I'm clamping, yes, when I'm the first string, when I'm clamping the first ball, well, the string I'm clamping to the floor, that's there. And this second string is for the second pendulum, the pendulum that is attached to the first ball. So here I have the 2 bodies. So they are making the string there. And here in the while, I am making the first ball, the second ball, the first string, the second string, and that's it. And here, in this case, you will see in a minute that having this here, the frames per second is important. to be relatively high. Otherwise, you need to apply the trick that Patrick also showed us to make more calculations compared with the numbers of frames that you are presenting, because otherwise you will be kind of dumping the string just because the integration procedure, the time step is too high, and it will be and the pendulum will start losing energy. So, but this is not the case. I put a still relatively high value, and my gravity is still a small. So if you change gravity here and the gravity is too high, also you are getting this this damping effect. So that means that the time step should be much smaller. Those are tiny things that you will need to pay attention. So I just started in a very special position where I'm adding this for the pendulum. So now the pendulum is in the chaotic region of the space. So it will be bouncing here. We can do more stuff here. So another thing that you can do is, for example, drawing, which is very nice. And you see, for example, in Wikipedia, they have another kind of a simulation where you see all those convoluted trajectories for the pendulum in the chaotic region. Again, this is something complicated to produce with a real life pendulum, because you need to be very careful trying to reduce all those frictions, all that stuff. But here we can simulate that, we can produce the plots, we can present the effects of this very simple and still very rich in the mathematics, in the possibilities of those chaotic systems. Another thing that you can do, which is kind of an exercise for this, it will be very, very nice, but the code, well, I didn't have the time for finishing. I also didn't have the time to present it. Is, for example, presenting synchronization effects. So you have two pendulums, or like and those are attached to a bar, and one pendulum starts synchronizing the other. So at the end, they will be working to at the same pace. Those are nice effects that you can add. Synchronization, another control of chaotic systems. So those are nice topics from they were very, very hot, let's say 10, 15 years ago when I was doing my PhD. All those things that you can introduce here in demos, they are nice for teachers. So that's all that we like to present. I don't know if we have here, is Logan around? No. Okay, so that means that is all that I have to present for today. Unfortunately, I was expecting Logan to appear, but he didn't show up. So I will be happy to entertain questions from you on this or our previous lesson, whatever you want. Otherwise, we will be finishing earlier today. I don't see Logan. Again, Daniel just posted the forms for filling your feedback about this workshop. So please feel free to fill the form, tell us what you like, what you would like to see better, with what kind of things you can change. You see, it's still my pendulum is no longer making twists. They is slightly slowing down, but that's because when you are dealing with chaotic systems, the integrator needs to be very special. So you need to be very, very careful with time steps, with the way you integrate those systems. So this is for no means a way of compute the trajectories. It's just for teaching a little bit the materials. Yes, you can add mass to those things. You can also replace the and I think I deleted. I was actually doing something like that. So I was adding mass to the to the bars, and also I was replacing those pin joints into damped strings. And I was trying to go the other way around, so you can put a damped string and put a very, very large young modulus to try to come back into this from the other side. And also you can put rigidity in the rotation. So you can put a few other things. So all that you see here are damped the joints. Oh, what? No, it's not. What? It's not this one. It's not here. Let me see if I can find. But yes, you can add those things, those properties to the graph. Yes, stiffness, for example, you can change that. But this is for the. This is, I think, this is for. Oh yeah, this is for the damped string. Yeah. So when you create the damped string, you have the young modulus and the stiffness here. So here, all those are all the properties that you can change. And here is the stiffness, which is the spring constant. So you can come back into this problem from the other side with a very, very largest and start changing that and see the spring jumping and adding all those things. So yes. Yeah, sure. Yeah. So they have several. They have okay. They also have this one, the damper rotary spring, spring, and the original here, which is, let me see if I can find. Probably it's down below the joints, because this is going alphabetically. So the gear joint here, and let me see, the grow occur joint and the pin joint. So yes, so all those things. And there is another thing that you can do, and it's combining all this stuff. Adding, for example, I never go into that, but it's something that also you can do. It's, for example, having here some text in the window, for example, monitoring the frames per second. Well, that's more a gaming-like thing that gamers like to see if the graphic card is producing the 120 frames per second. Well, that is something that my son will love to see. But apart from that, from the physics perspective, you can see here, for example, putting kinetic energy, temperature, the total energy of all those particles. So you can put things like that, and also you can make the simulation react to mouse effects. So you can drag, for example, there are examples in the documentation where you can drag the ball and stretch it, and so with this you will be allowing the users to interact with the window. That's another thing that you can do. And yes, so all those things you can make this. And there is another thing. If you want to do this more appealing, you can replace those balls. There is another example, more for a gaming like, but this is in Pygame. So instead of drawing a ball, you can just draw an image of a ball. So you pick an image, a PNG file, where the corners are transparent, and with that you can have a ball, like a billiard ball or something, and with this you put a representation that is nicer, more appealing for kids. So that's another thing that you can do. But that is more for Pygame. So PyMonk will be dealing with the machinery, with the engine, the physics engine, which is very, very hard to code, let's say, properly for those particles effectively. And the Pygame will be making the plot of that. Another thing that you can do is, and I never did it before because just with 400 particles and more normal computers don't care too much about that, is that when particles escape so for example, the Y position of the particle is negative, for example, so the particle go away, just remove the particle. That makes the simulation more fluid, especially if you are generating particles all over again. So you need a procedure to also remove those objects from your stack, so you don't get like an explosion of your memory, and also the explosion of computing all those positions that you will never see. So that's another thing that is in the examples. I think it's one of the examples where you are removing particles from your stack, from your objects, from your list of objects in the script. So all those things. Okay. What we have? Okay, in that case, I will be closing earlier, unfortunately, but I don't have what I would like to show you from PyVista. The person who was giving that didn't show up. So I will say thank you for attending all those workshops all these days, for your patience and understanding these days, and everything that we would like to show you. And we will probably we will present another workshop in October, and sometimes we present something around November, but not necessarily this year, but maybe we will make another introduction to HPC. We will see. So we can have another like a winter workshop. So thank you very much. I will be stopping here. I will stop sharing here.